Hello, everyone. As we follow our retreat week, we have another session with a guest speaker today, Yi-san, who is going to be giving a talk on Halo 2 based aggregation and recursion in Axiom version 2. Welcome, Yi, and the stage is yours.
Hey, thanks for inviting me to speak here today. I'm going to talk about how we use aggregation and recursion and connect that to the end developer experience in Axiom V2. So first of all, just going to do a brief introduction to what is Axiom and what's the end developer flow that we're trying to enable with aggregation and recursion. So what we provide at Axiom is a way for smart contracts on Ethereum to do compute over the entire history of Ethereum. And so the way that works is that developers can specify the data they want to access and compute over using our TypeScript SDK. You can see a sample TypeScript file on the right. You can try it out for yourself at repl.axiom.xyz. You can see here that we allow users to access, for example, historic accounts or and inputs from those accounts like balances through functions like getAccount. And then we allow users to do some computation over that through functions like add or diff. And so the entire history of Ethereum is available in this way, including transactions, receipts, and all other data that you're familiar with. And at the end of the day, we will give a ZK verified output to a developer smart contract through a callback. And so in particular, we want to avoid the requirement that the developer actually deploy any ZK-related verifier functions. All right, so let me talk in a bit more detail about how that actually works, both on the ZK and interface side. So the flow is that a developer will submit an on-chain query to Axiom, and that's going to trigger the proof generation of an aggregate ZK circuit that combines two things. First is the validity of the computation. And so that is what is specified in our TypeScript SDK, which specifies a custom computation subject to some claimed values of historic on-chain data. Now, this circuit doesn't actually verify that those values are correct. It just says, assuming, let's say, your account balance was what we claim it is, then the average of your balance is what we claim it is. Now, of course, we then need to prove the actual authenticity of this input data. And that's done using the data circuit. So that proves that the claimed historic on-chain data really was authentically committed to in some commitment to the Ethereum history. Now, of course, to get the statement we want, which is that we correctly computed over the Ethereum history, we need to combine these two statements. So that's the function of this overall aggregate circuit. Okay, so let me talk a little bit about sort of the root of trust that we're using to actually authenticate on-chain data in ZK. So there's two steps to this. So whenever we prove some historic data access, we prove relative to a commitment to all previous block hashes on Ethereum. Now, as you guys know, in Ethereum and any blockchain, the current block commits to the previous block by containing the hash of the parent block. And that continues all the way back. So the previous block commits to the block before that, and all the way back to Genesis. Now, what that means is to show that a historic block hash was truly present in the history of Ethereum, one would need to prove a Keccak chain of block headers between that previous block and the current block. And so that's pretty expensive to do every time. And so what we do is maintain a Merkle mountain range of all historic block hashes on Ethereum in a smart contract on Ethereum. And every time new block hashes appear, we generate a ZK proof that we are correctly updating this Merkle mountain range from what it is right now to the new value. And we're going to use this Merkle mountain range as the root of trust for all our data proofs. So what that means is that to prove, let's say, a historical receipt was really present in a block from 1 million blocks ago, what we need to do is check a Merkle proof for that receipt into the receipt trie, and finally, that receipt's root was present in a historical block header. So these Merkle proofs are pretty large, and we compress them by proving their verification in zk. And so in this way, we're actually able to access all historic on-chain data into this Merkle mountain range. Okay, so there are a number of kind of challenges in the developer experience when creating such a system. And I'll just talk through what we see as the main ones. Tedab asks, how can you avoid inserting a fake block hash in the Merkle mountain range? That's a great question. So the root of trust of the Merkle mountain range, which is, let me go back, is the EVM access to recent block hashes. So EVM has native access to the last 256 block hashes through the block hash opcode. And when we generate a zk proof to extend the Merkle mountain range, what we're showing is that there is a most recent block hash that the EVM must have access to. It commits to a chain of previous block hashes, up to 1024 of them. And then we can correctly update the Merkle mountain range using that chain of block hashes. So at the end of the day, the guarantee that we're providing is that anything that we're putting on chain through Axiom should either be verified through an EVM opcode or in zk. Yash is asking, are the old Merkle roots stored too? Yes, the old Merkle roots are stored. And I didn't talk about this here, but when we first deploy the contract, we need to do a bootstrapping procedure. What that means is that we need to prove that in chunks of 128 times 1024, that the block headers of Ethereum commit to each other and form the starting Merkle mountain range. So the way that works is when we deploy the contract, we can, in the EVM, check the last 256 block hashes. We then record in our contract which block hashes we have already committed to and verified through either the EVM or zk. Then we can start proceeding backwards from those hashes all the way to Genesis. Pia asks, isn't this limited to the latest 256 blocks? Yeah, so the answer to that is the EVM can only access the latest 256 block hashes. But once we've accessed one of those, we can decommit all previous block hashes from that one. And so that's kind of exactly what we do. Any other questions about this Merkle mountain range construction? All right. Okay, so we have this construction where we can generally access historic data by doing Merkle proofs into a cache of Merkle mountain range cache of block hashes. In this setup, there are quite a few sort of developer experience challenges when you actually want to make the system usable by smart contract developers. So I'm going to talk through 3 of them that we found to be the most pressing. The first is that when you look at the actual workloads that developers are interested in, they have pretty dynamic usage of what we call subqueries, which are calls to different types of data. So developers might want to access, some receipts, and then some contract storage, and then maybe an account balance. So it's pretty heterogeneous. And also different queries want to access different amounts of data. So one type of query might involve 2 receipts, another might involve like 1,000 storage slots. So we have to kind of adapt our system to this dynamism. The second challenge is that users sometimes care about very large queries. So within one query, they might want to access 10,000 storage slots. And so that might be too large to fit into a single zk circuit or to do proof generation onto a single machine. And so it's important for us to be able to scale the system to meet those needs. And then the last thing is that the developer requests are pretty heterogeneous, and developers really want to specify the way they combine the historic data in a very custom way. So if you imagine something like just contract storage, it's pretty easy to parameterize that. You have an address, a block number, and a storage slot. But when you want to do something like an average over a user's ERC20 balance, you quickly realize that it becomes pretty complicated. You need to check that you're getting the contract storage for the same contract at evenly spaced block intervals. And that last phrase, the same contract at evenly spaced block intervals, fundamentally is a pretty basic form of compute. But if you try to design an interface for that, you'll quickly realize that you actually need to allow somewhat arbitrary computations. And so I'll talk through how we actually use aggregation to address these three types of issues. And so I think I already talked to that the data that we're accessing is heterogeneous. Each type of data requires a different circuit for us because they're committed to in Ethereum in just kind of different ways. And so we divide that data into 6 types. There's block headers, accounts, storage, transactions, receipts, and solidity mappings. All right, so before going through the actual usage of aggregation, I just wanted to talk through the end user flow that we've come up with to address these issues. So the way it works is there's sort of 5 steps. So we start, so Pia asks, what's the difference with solidity mapping and storage? Yeah, that's a great question. So in storage, we simply allow you to specify a storage slot and give you the actual value. In a solidity mapping, let's say you have a mapping between address and uint256. Then for every given key, solidity actually determines a storage slot associated to that key. That's sort of determined by a catch-act hash of the key and the slot of the mapping. And so, of course, you can fetch any single key value lookup using just a call to storage. But what you need to do is to compute the storage slot using a catch-act hash. And what we found is that when you end up wanting to do this, let's say 100 times or 1,000 times, that the determination of the storage slot for a given key starts becoming a limiting factor, and you end up not wanting to do that on-chain. So we provided a kind of generic interface that you can handle like the nested mapping access also within ZK. Yeah, so Ted, it's exactly like a helper for accessing nested mappings. Yeah, so you categorize static storage value as storage and dynamic storage value as solidity mapping. Not quite. I guess for us, storage is just a direct read from the contract, from the storage trie. And then solidity mapping is a specific parameterized way to read into that trie that takes into account the way that storage slots are computed for nested mappings in solidity. I guess maybe I'm not so sure what you mean by static versus dynamic.
I think we can go forward.
Yeah, go ahead.
I think we can go forward.
Oh, cool. Yeah. Yeah, so to go through the overall flow that we're enabling, it sort of has 5 steps. So basically, we enable our developers to export a client-side ZK prover that will generate the compute proof. So remember that this is a proof of the computation subject to claimed values for on-chain data. And so it's actually light enough to be run in the web browser. And so you should think of this as something that can plug in to the developer's web app. From that, a user can send a query to our contract on-chain, and we're going to index that query, which consists of the proof and a request for on-chain data. And on our proving server, we will generate a data proof, as well as an aggregation of the compute proof and the data proof that checks up all the claimed on-chain values actually are correct relative to some commitment to the history of Ethereum. So in this case, our commitment is just the Merkle Mountain range. Then we send that aggregate proof to our on-chain contract, and in EVM, reconcile that the Merkle Mountain range we're proving relative to really was committed to in our on-chain contract. So in certain cases, this is just an equality check. We check that the Merkle Mountain range that we store in the contract is the same as the one we proved it to. But in other cases, it might be a little bit more complex. For example, if we want to prove into a Merkle Mountain range that's slightly more recent than what's stored in our contract, we can actually dynamically extend the Merkle Mountain range in Solidity and check that the extension of the Merkle Mountain range in our contract is the same as the one we proved into. So this verification logic gets a little bit complex, but in all cases, we handle it so the latency is kind of minimized for the user. Once the verification is done, then the values are sent to the smart contract developer's contract, and they can apply their actual application logic. All right, so let me now talk through sort of the two pieces that kind of enable this. The first is what we call the components framework, which is our general way of handling cross-circuit calls and aggregation within Halo 2. Okay, so our goal in the components framework is to create a type of circuit which we call a component circuit. And what we want to do is to allow those circuits to make external calls to other circuits. So as a generic example, you could think of the user's compute circuit making external calls to other circuits that are going to verify the authenticity of data inputs. So you might make an external call from your, or we call it a promise call, from your compute circuit to our receipts component. And so we're going to divide every component circuit into a couple pieces. The first is the part of the circuit that's just the component-specific logic. So for the receipts component, it would just contain receipts proofs. Or for the block header component, it would contain RLP parsing of the block header. Now, within the circuit, we allow the component to make what we call promise calls. So these are, it's kind of like, these are named in analogy to promises in TypeScript or JavaScript. The idea is that these are claimed input-output pairs for other functions that must be verified later in aggregation by a separate component circuit. And finally, a component circuit is allowed to expose a virtual table. That's sort of the input-output pairs of functions that the component circuit itself is computing. For example, for the catch-up component, this virtual table would consist of the inputs and catch-up of those inputs. And so the idea here is that the component logic is supposed to constrain the correct values of this virtual table. And the virtual table is just going to be a list of key value pairs that have a functional relation constrained here. We allow the key to be variable length, but the value must be fixed length. So you might imagine that the key is an input to the catch-up hash, and the value is the hash. So yeah, the way we actually expose this table is by committing to this list of key value pairs. And so we either just use the Poseidon hash, or we use a Merkle root of Poseidon hashes. And so this shows that actually a component can be fulfilled in multiple ways. Here we could either have a single circuit, or we could have an aggregation of several single circuits. So for example, for catch-up, if we just want to compute maybe 10 catch-up hashes, we can do that in a single circuit. If we wanted to compute 10,000 catch-up hashes, we would do that in an aggregate circuit. And so the main idea of components is that we allow some of the components to use promises proven by other components. And there, the way this works is that we take the virtual tables exposed by those other components and read them into materialized tables inside the component logic, and then use dynamic lookup to read from those tables. So just to give a sense of how we actually use this in our data circuit, we have 6 circuits for each of the primitives, so block header, account, storage, and so on. And they actually all make promise calls into our aggregate catch-act component. And finally, we need to take all the components, circuits, and promise calls and verify that they were correct within an aggregation circuit. And the aggregation circuit is very important here because it checks that all the promises were actually correctly fulfilled. For example, it would check that the account circuit, which has a promise call into the catch-act component, as well as the block header component, actually had correct virtual table reads from both of those components. So you might imagine for an account proof, you need to check that the state root, which is the root of the state trie, is correctly represented in a block header. And then you also need to check a bunch of usages of catch-act in your Merkle proof. And so that's exactly what's checked by these promise calls. Okay, so let's see how the components actually address the considerations that we were mentioning earlier. So the first thing is that it actually dramatically cuts the cost of dynamic subquery counts and sizes. And the reason is that if you have the dominant cost for us is using catch-act, is verifying the catch-act hash. And so this allows us to share the cost of the catch-act hashes between all subqueries. And further, if we allocate space for subqueries, let's say an account proof or a storage proof that we end up not using, then the evaluations of catch-act that they do are going to be repeated. And in this case, we don't actually repeat the row in the catch-act component table. We just have one row for that evaluation. And that means that actually the unused and repeated evaluations impose 0 marginal cost for us. And that means that we can actually have dynamism with very low overhead. Secondly, for scaling to larger queries, well, by having this component framework, we can actually prove the circuits for the different components on different machines. And in particular, in the catch-act component, which is the limiting factor for us, we can prove multiple catch-act tables on different machines, and then finally aggregate them into one that fulfills the promise. So it gives us this kind of homogeneous interface for accessing circuits, which could either be single circuits or aggregation circuits. And so that lets us actually scale out across many machines without changing our ZK interface sort of in any way. All right, so there's still one remaining issue, which is that the aggregation structure is fixed in this setup. So if I have a different developer-specified compute circuit, then it's going to access different types of subqueries. And the final aggregation circuit that's supposed to reconcile everything is going to be different depending on what the developer has requested. So that's pretty unappealing, mainly because on the proving side, we would need to scale out our prover in a very custom way for every developer. And that's a pretty big challenge on the backend. So let me now talk about a feature we developed to address this issue, which is called universal aggregation. So to do so, let me talk about sort of how aggregation works just in general, and then how we can make it universal. So in Halo 2, what the general procedure of aggregation does is you have a proof, and you have a fixed verification key for that proof. And an aggregation circuit takes in that proof and checks that it verifies against the verification key, subject to a deferred pairing check. And when we're verifying an EVM, we always do this pairing check on-chain. Now, what we mean by universal aggregation is that we want to enable this verification key to actually be different between runs of the circuit. So we change the V key from fixed to variable. And what this universal aggregation circuit is going to check is that the proof verifies against the variable V key with a deferred pair. Now, there's some subtlety in that if I didn't have this box, which I've labeled V key hash, then the output of the universal aggregation circuit would actually not be that helpful. And the reason is that it's definitely not helpful to know that there's some hidden proof that verifies against a hidden V key, since those two could both be literally anything. So instead, what we need to expose as a public output to allow the user of this aggregation circuit to actually understand something about what was proven is a commitment to the V key that entered. And so we call this a V key hash. So for us, a universal aggregation circuit takes in a proof and a V key, checks that the proof is valid relative to the V key, and outputs a commitment to the V key. And here we use a simple hash, but you could use any commitment. And so the way that we use universal aggregation, which we've actually implemented, is that we take in a compute proof and a data proof on the server side. So remember, the compute proof was given by the user as part of their query into Axiom, and the data proof was generated on the server to verify the on-chain data primitives that the user requested. We compute both of these and send them to universal aggregator. And so what that is going to check is that first, the compute proof was actually valid relative to a variable V key. Second, the data proof is actually valid against, again, relative to a variable V key. And finally, that it's going to output an aggregate proof plus a commitment to the V keys that were used in this aggregation. And so this commitment is actually going to commit to the compute circuit that the developer used, as well as the pattern of aggregation which entered into the data proof. And we actually set this up so that this proof can be verified against a universal on-chain verifier. So for the developer at the end of the day, you get a proof that can be verified against a fixed smart contract on-chain, and you get an identifier of the exact query that the developer was making and the aggregation that entered into its fulfillment. And so long as a developer trusts this commitment, then they don't need to make any additional trust assumptions or deploy any custom verifiers to use Axiom. And so we think it's actually pretty important to cut out this step because it makes the flow much more similar to standard smart contract development than something really specific to ZK. And so ultimately what this means for the developer is that in order to actually use results from Axiom, all they need to do is implement a single callback function that receives the results. It actually validates these commitments to the compute circuit and the aggregation structure. So you can see we send the developer a bunch of data. We send them, some bookkeeping stuff like the source chain that we were reading from, the caller of the request, and then some crucial fields, which are called the query schema and the query ID. Schema is a commitment to the verification key of the compute circuit, and the query ID is a unique identifier of the proof that is being validated here. And so for the developer, if they check that the query schema is equal to the one that they requested, then they'll know that this callback is a result from a query of the form that they expected. And that means they can use the results in Axiom results to perform the standard application logic. Tadev asks, I'm not sure I understand the need for V key hash. Isn't the V key of a circuit public anyway? Yes, so in this case, the V key of the circuit is not public. That's exactly why we need to expose the V key hash. And let me explain why that is. So within a normal aggregation circuit, we have a ZK proof, and then we have a fixed V key, which means that it's public. Now, when we make it universal, we're going to make the V key variable, and then we could choose to make it public, but the V key is pretty large, so it's undesirable to make it a public output. Instead, we want to make something a bit smaller public, which we call the V key hash. So you're definitely right that if we made this variable V key public, then we definitely don't need to hash it. But it ends up being only necessary to make its hash public. And the downstream consequence of that is if we instead had made the full V key public, then instead of a single bytes 32 query schema, we would have a pretty large bytes 32 array that the developer would need to validate. And so that's pretty costly gas-wise, which is why we opted for the hash. PS is aggregate, meaning doing some computation, like sum, average, etc. Now, so here aggregation is a ZK term, which means that which means any procedure where you take one or multiple ZK proofs and check that all of them validate against either fixed or variable V keys. So here I've shown aggregation with just one proof, but you can imagine multiple proofs. And so in our actual usage, we will do aggregation over many proofs. So you can see in our components framework, we would have one proof for each type of on-chain data and one proof for Ketchak. And the proof for Ketchak itself would be an aggregation of multiple Ketchak proofs. And so this outer aggregation circuit would check that all 7 of these proofs are valid, and also that there's a bunch of compatibility conditions between their public input outputs. And yeah, I can't go to the link right now, obviously, but I think, yeah, that's definitely, I think that's basically what we're referring to. Cool. So just to sort of wrap up what we're actually getting from this universal aggregation, there's sort of 2 advantages. So the first, which I already sort of talked through, is that we can allow the developer to specify the computation. And subject to some size limits, we can handle all computation circuits that the developer specifies using the exact same on-chain verifier. And so this really simplifies the deployment. The second thing that's a little bit interesting is that with the developer circuit, because we put it into a TypeScript package that developers can run through WebAssembly on the browser, is that it actually can be proven client-side. And so it turns out that any private value there actually is private. And so we can enable developers to have some notion of privacy in their application. The second advantage, which is maybe a little bit less obvious, is that because the aggregation circuit is universal, we can use different aggregation configurations depending on the number of subqueries that are used. So just as one example, you might imagine one type of query only uses receipts. So maybe it asks for 100 receipts, whereas another type of query only uses contract storage, let's say 1,000 storage slots. This setup actually allows us to use completely different aggregation configurations for those 2. So for the receipt setup, the circuit might only have 100 receipt subqueries, whereas for the storage setup, maybe it only has 1,000 storage subqueries. And so we can handle all of these in a uniform way through using different universal aggregators. And so that means that to the end developer, the only thing they see as a difference is that there's different commitment of aggregation structure that they receive to check as a hash. But the entire on-chain flow and ZK flow behaves totally uniformly. And so we think that's a good way to actually allow this flexibility on the back end for better performance while maintaining a uniform interface at the smart contract level. All right, so that's just a brief overview of the two ways we're using aggregation at Axiom. If you want to try out the end consequence, you can check out our SDK at repl.axiom.xyz. We also have a starter kit if you prefer the command line, and you can check out our developer docs for that. Tanav asks, why would the user need privacy? Isn't the data going to be used eventually on-chain and has to be public? The answer to that is the output is definitely going to be used on-chain and has to be public, and the on-chain data is definitely public. But what we can make private is some potential user-specified private inputs. As an example, this one would enable the usage of nullifiers. So you're definitely right that anything that touches on-chain data or has results at on-chain, that is all public. But the input might be private. Ali asks, is the hashing of V key itself checked in the circuit? Yes, so in the universal aggregator, the hashing of the V key definitely needs to be enforced in the circuit. So the V key would be a private input, but the hash of the V key would be public. He asks, is the aggregation in universal aggregator only in Halo 2 proofs, or do we allow other proofs as options? Today, we're only allowing Halo 2 proofs. And the reason for that is just the aggregation of Halo 2 proofs is actually a little bit different than other proofs. We have developed a component that does Groth16 aggregation. Turns out it's actually very simple to do, maybe like 20 lines of code. So yeah, we're thinking through like our product plans for that. Question, can you elaborate a bit more on deferred pairing? Yeah, so this is the part that's actually a little bit different between aggregating Halo 2 proofs and other proofs. So the idea here is that we are in a setup where we are trying to do aggregation of a proof from Halo 2 with the KZG backend in Halo 2 with the KZG backend. So when you actually write down the full verifier for Halo 2 with the KZG backend, you'll find that there's kind of two pieces. One piece is to do a certain MSM or a couple MSMs that depend on your proof values and your verification key. So we do that check in the circuit. Now, the second step is to do a pairing check based on some elliptic curve points that you derive from the MSM. And we actually defer that, meaning that the statements that our circuit proves is that if you believe this pairing check held, then you should believe the proof. And that deferred pairing, the reason we defer it is that we can almost get it for free by combining it and doing it simultaneously with the pairing that's involved in the verification of the aggregation proof itself. And that check is ultimately going to be done on-chain in the EVM. So just to maybe explain like the difference between that and how we would do, let's say, recursive verification of Groth16 proofs. And this is why I didn't say recursion. If we wanted to verify a Groth16 proof in Halo 2, well, Groth16 verification has the same structure. You do some MSM and you do some pairing. But in this case, because the structure of the pairing is actually not the same as the one in Halo 2, what we need to do is check the MSM and the pairing in circuit. And so that's obviously just a little bit more expensive. Yeah, so is aggregating proof the same as recursive verification? It's the same goal, but there is just this subtlety of whether the pairing is deferred. So in general, like aggregation refers to this procedure of doing part of the recursion, but leaving some marginal work for the end decider. And what makes something an aggregation is that the work for the end decider is somehow very cheap, something like O of 1. So maybe like other examples of aggregation would be something like folding, where the procedure of folding proofs is pretty cheap, but then the final verification, you are accumulating a little bit of cost. Ali asks, how do the users of Adapt check that the circuit the devs use wasn't changed, given that the V key is private? Yeah, so this is exactly the reason why we have this V key hash. So the V key hash is public. And so the users just need to check that the V key hash is not changed. And that's actually exposed on-chain. So our belief is that it's easier for users to check some hash that's just actually checked by a smart contract than to look at a full V key on some website or something. Yeah, question. How different is Axiom's fork from PSC's? So yeah, this is talking about we maintain some fork of Halo 2, and it's actually based on PSC's fork. The answer is, and we get this question a lot, it's not really different. As in, the proofs generated from our fork will verify on theirs and vice versa. We just put in a few sort of performance-related hacks that they probably don't want to upstream. So we maintain kind of byte level compatibility. Like we think there are already too many Halo 2 forks, and we're not trying to add to the problem. Yeah, there might be some sort of versioning timing changes as well. Like they're a little bit more aggressive with bumping versions of dependencies, whereas we want to be more conservative because we have production code that's already been audited, and so we've frozen the versions of some of the dependency packages. So at certain periods of time, we actually will lag behind them. But fundamentally, we will always be byte level compatible at the proof level with proofs generated from some version of PSCs. Xerox Nagu asks, when the final smart contract that verifies a universal aggregation, what is being proved and verified? Yeah, I mean, at a high level, it is like the full computation. So what I mean is at a high level, it's that, hey, the computation you did is correct. The data inputs are actually correct relative to, maybe it's useful to talk about the public outputs. The public outputs would be a commitment to the full aggregation structure and all the verification keys that appeared in the aggregation structure. So that is actually very important, and you really need to check that that commitment is what you expect, since that it controls the content of the proof that you're verifying. After that, supposing that that is one of the ones that refers to our whole aggregation structure, then it's proving that, hey, you had a user-generated proof of your computation that shows that given subject to some on-chain inputs, the final computation output is what you expect. Second, that those on-chain inputs really were committed to in some claimed Merkle boundary range, which itself is public input. And so yeah, so like the inputs are basically what is the developer's query, the result of the developer's query, and then the root of trust for the developer's query, which in this case is a claimed Merkle boundary range of block hashes. And so in the final smart contract, we verify the ZK proof. We check that the commitment to the aggregation V keys in the ZK proof is on a whitelist, which is a list of ones that refer to our structure. And then we need to check that the Merkle mountain range, which roots trust for the data, is actually committed to in our existing on-chain Merkle mountain range. So if all of those pass, then this would prove like, hey, the computation the user wanted over the history of Ethereum was correctly computed. General question, what do we think about VM versus circuit approaches to proving general compute? Yeah, I mean, I think both are kind of valid. We think of it kind of like as it's not too different from, I think, computer hardware. Like there's going to be a gradation of approaches depending on, your developer input and the end efficiency. So basically, it's not really possible to ever beat handwritten circuits for specific computation. Just like in normal computer hardware, ASICs will always be the fastest way to do a specific computation. Now the question is, in different circumstances, how do you care about developer flexibility versus performance, and how can you create systems that kind of trade off both? So definitely VM is going to be better in terms of developer flexibility. I think you do take on a lot of overhead by actually doing a VM. But the other thing you take on is you're exposed to the compiler tool chain of that VM. And I think that's actually the biggest complexity that you take on.
Yeah, I guess if there are no more questions, we can wrap it up. Thank you, Yu. That was really interesting.
Yeah, thanks for having me, everyone. And thanks for all the questions.
Thank you. Thank you.